Can we start?
Yes, ma'am.
Okay. Are you able to see my slides?
Yes, ma'am.
Okay. Good evening. Welcome back to NPTEL PMRF tutorials on Introductory Organic Chemistry 2. Myself Anisha Suresh, PMRF TA for this course from IIT Bombay. So last week we have discussed about week 2 assignments of previous year. Today we will be discussing about week 3 assignments. So, is there any doubt regarding week 2 assignments that we have discussed last week?
No, ma'am.
Okay. Now, can we move towards question 1?
Yes, ma'am.
Okay. So, this is question 1. They are asking for what is the correct order of equilibrium enol content of the following compounds. So, here there is ketone in all the systems. So, there can be possibility for ketoenol tautomerism. So, in which of the cases this enol content will be more? That is the question. So, we know that uh, for the enol content to be more, the factors that determines are resonance, aromaticity, hyperconjugation, polarization, and many other factors. So, coming to our question, here in these four options, there is a possibility for resonance stabilization in this three cases: B, C, and D. And out of B, C, and D, this C will be having more hyperconjugation effect because of this medial substitution. Here, ketone is having medial groups, so there will be more hyperconjugation. So, hyperconjugation increases means enol content will be increasing. In these cases, there are medial groups, so hyperconjugation will be increasing. As a result, enol content will be more. And these three are more favored than this A because there will be resonance stabilization because if anion is generated here, it can undergo resonance with this ketone as well and this ester as well. Similarly, here both ketones and here aldehyde and ketone. So compared to A, B, C, and D will be having more enol content. And here also they can form hydrogen bridge. If enol is forming, hydrogen bonding can be resulted. One, two, three, four, five, 6 member transition state will result in all these three cases. Uh, Able to follow? I hope so. Here, out of these four, A will be having least enol content, and we have to sort out like out of these three, which is having more enol content. So here, C will be having more enol content because there will be resonance stabilization. Also, there will be hyperconjugation effect from these medial groups. Here, there is hydrogen only, so hyperconjugation effect won't matter. So out of C and D, C will be having more enol content, and this B is ester. So esters will be less stabilized because compared to ketones and aldehydes. Enolates of esters are less stabilized compared to ketones and aldehydes. So the correct order will be here C, which is this diketone greater than D, then B, and finally A. Is this clear?
Yes, ma'am.
Okay. Now we can move towards question 2. Here they are asking for which of the following equilibrium the KEQ is less than, excuse me. So now we are discussing question 2, and they have asked for which of the following equilibrium this KEQ is less than 1. So we know that we know the definition of K equilibrium. K equilibrium is if there is an equilibrium existing between starting material and products, then KEQ will be concentration of products divided by concentration of starting materials. So if KEQ is less than 1 means the concentration of starting material will be more. That means starting material is less prone to react to form the product. So we can see all the four options. Here they have given a hexafluoroacetone derivative. Here a hexachloroacetone derivative. Here acetone, and here a fluoro substituted formaldehyde. So these they have given examples for hydration reaction and asked for in which of the cases KEQ is less than 1. That means in which of the cases the starting material is less prone to react to give this hydrate. So we can, as we have discussed, for the equilibrium, A reacts to give B. The equilibrium constant K equilibrium can be written in this form. K equilibrium is concentration of product, which is this here. A is the reactant and B is the product. A is the reactant and B is the product, and so KEQ can be written as concentration of product divided by concentration of reactant. Here, this form represents a concentration of A at equilibrium. So, in case of at equilibrium, if the concentration of B is more, that means KQ will be greater than 1. So, in our question, they have asked for cases where K equilibrium will be less than 1. And here are some equilibrium distribution of some common aldehydes and ketones forming hydrates. So in case of formaldehyde, here the electrophilicity at this carbon center will be more, because these are two hydrogens, and that does not affect the electrophilicity at this carbonyl center. So it can easily react with water and form this formaldehyde hydrate. But in case of acetaldehyde, here there is medial substitution. So medial group is electron donating group. So because of its electron donating nature, here this electrophilicity will arises because of lack of electrons. So these are donating electrons, so that electrophilicity at the center will decrease. So it will have less chance to react with water and to form this acetaldehyde hydrate. Because of that, 42% acetaldehyde will remain in that system, and 58% will transform into acetaldehyde hydrate. And in case of acetone, there are two methyl groups. So two electron donating effects will be coming into picture, and this electrophilicity at the center will drastically decrease. So this will be less prone to react with water to form this hydrate. Because of that, acetone will be present majorly in the system, and acetone hydrate will be present in very less amount. Coming to then, so as we can see, the addition of electron donating alkyl groups which stabilize the positive charge on carbonyl carbon decreases the amount of gem diol product at equilibrium. So hydrate formation will be very less facile when there are electron donating alkyl groups present in the system. The addition of strong electron withdrawing groups destabilizes the carbonyl group and tends to form stable hydrates. So if this methyl group is substituted by a trichloro substituted methyl, it is highly electron withdrawing in nature, and because of its electron withdrawing effect, this is already having delta positive charge, and when from there electron is withdrawn, that positive charge will increase and it will become unstable, and it can easily react with this water to give this hydrate. Is this clear?
Yes, ma'am.
Okay. Now coming to our question back, here we can see this is trifluoro substituted methyl groups, and we know that CF3 is electron withdrawing in nature. So it will be high. Two CF3 are there. It will be highly electron withdrawing in nature. So this will be a more electrophilic sender, and it can easily react with water and form this hydrate. So here the product concentration will be more. So K equilibrium will be greater than 1. Is this clear?
Ma'am, once again repeat that, ma'am.
Okay. Here we can see this is the carbonyl sender where this water molecule will come and attack. This is the electrophilic sender. This carbon is the electrophilic sender. So it is already having delta positive charge, and if some electron withdrawing groups are present adjacent to that carbonyl sender, they will push electron density towards them, and because of that this carbonyl sender will become more electrophilic in nature. So it can easily react with this water molecule and result in formation of this product. So here the concentration of product will be more. So we know that K equilibrium means concentration of product divided by concentration of reactants. So if concentration of product is more, that means if concentration of product is more, that means K equilibrium will be greater than 1. Is this clear?
Yeah, ma'am.
So because of that we can eliminate this option. Here K equilibrium will be greater than 1. Similar is the case with this system also. This trichloros hexachloro substituted acetone. Here this CCl3 group is also electron withdrawing in nature. So this carbon sender will be more electrophilic. Water will attack and it will easily give this hydrate. So this here product concentration will be more. Because of that K equilibrium will be greater than 1. So this option also we can eliminate. Then coming to this option, last option, here this fluoro group is electron withdrawing in nature. So it will pull electron density towards it. Because of that, this electrophilic sender of this carbonyl will be turning more electrophilic in nature, and water can attack and give this hydrate product. And because of that, here K equilibrium will be greater than 1. Hydrate product concentration will be more compared to the aldehyde, and because of that K equilibrium will be greater than 1. So we can eliminate this option. Now coming to acetone, as we have seen, here two electron donating medial groups are present. So this is electrophilic sender. It is lacking electron density, and some electron withdrawing groups are present nearby, means it is donating electron density to that electrophilic sender. So that positive charge will decrease, partial positive charge will decrease, and because of that this attack by water will be less facile there, and formation of this hydrated product will also be less facile. So here the concentration of reactant will be more compared to that of product. So as we have seen, K equilibrium means concentration of product divided by concentration of reactant. Here concentration of product will be less. So if product concentration is less, then K equilibrium will be less than 1. So the correct option will be this one. Is this clear? Hello?
Yes, ma'am.
Okay. So can we move to question 3? Hello?
Ma'am, if you don't mind, please repeat the reason for third option, ma'am.
This option. Okay.
Ah, yeah, ma'am.
Actually, these two medial groups are electron donating groups. And here this carbon sender is electrophilic in nature. That means it is lacking electron density. It is having delta positive charge. Delta positive charge. So there is delta positive charge, and if electron density is donated towards that sender, that delta positive charge will decrease, right?
Okay, ma'am.
If that positive charge is decreasing, then this electrons from water will be less facile to come and attack at the sender, because it is not that positive charge. Like if it is electrophilic sender, then nucleophile can come like and attack very fastly. Here that electrophilicity is decreasing, so nucleophilic attack will be less facile. Getting?
Okay, ma'am. Yes, ma'am.
Hmm. So because of that, this will be less reactive. Reactivity rate will be less, and at equilibrium, concentration of starting material is more compared to that of the product. So concentration of product is less. Concentration of product is less means, according to K equilibrium, concentration of product divided by concentration of reactant is K equilibrium. So if concentration of product is less, then K equilibrium value will be less than 1. If something more than 1 is at the denominator, then the value will be less than 1. Clear, right?
Yeah, ma'am. Now it's clear, ma'am.
Okay. Now we can move to question 3. So here they are asking, which of the following observations does not establish the existence of ketoenol tautomerism in acetone? So they are asking which of the following observation does not establish the existence of ketoenol tautomerism in acetone. So when treated with DCl in D2O, hexadeuterated acetone is recovered. That is one option. Then when treated with D2O bar NaOD, hexadeuterated acetone is recovered. Then third option is when treated with dilute H2SO4 in H2O O18, this isotope of oxygen, then this acetone with oxygen 18 isotope is obtained. And the fourth option is all of the above. So we can see options one by one. When treated with DCl in D2O, hexadeuterated acetone is recovered. So as we know, like in presence of acid, ketone and enol form will be like in equilibrium, as we can see here. Here this ketone, like this deuterium can coordinate with this oxygen, and it can result in formation of this enol form, where hydrogen is substituted with deuterium. So when this comes back to like according to arrow pushing mechanism, this falls back, then it will attack. So here instead of water there is D2O. So instead of abstracting proton, it will abstract D plus. So if it is repeating multiple times, hexadeuterated acetone can be recovered from the system. So this option can establish the existence of ketoenol tautomerism in acetone. Is this clear?
Yes, ma'am.
Hmm.
Once again, repeat, ma'am.
Actually, in like it is acidic system. So in acidic system, enol and ketone will be in tautomerism. So here, this is our ketone. It can coordinate with deuterium plus, and it can undergo tautomerism to give this form. Like here this proton, it will be eliminated. This will exist in this form. So when this form is falling back, like this enol form, when falling back to ketone, it can abstract a proton. Like here, this double bond will be converting into this CH3 by abstracting a proton. But in this system, it is DCl in D2O system. So there will be no proton. Instead of proton, it will abstract D plus. That is deuterium plus. So if this is repeating like multiple times, there will be hexadeuterated acetone formation. Like once this deuterium is abstracted, again there will be proton in acetone that will be abstracted from the system, and when this form is coming back, it will abstract deuterium from the solvent, and finally we will be able to obtain hexadeuterated acetone. So this option is like it can establish the existence of ketoenol tautomerism. So this option will establish the uh, existence of ketoenol tautomerism in acetone. This is clear, right?
Yes, ma'am.
So coming to our second option, so this will establish. So they are asking for option that does not establish. So we can rule out this option. So coming to second option, when treated with D2O bar NaOD, hexadeutyrated acetone is recovered. So this is basic condition. In basic condition, like keto and enolate form will be in equilibrium, like that will be in tautomerism. So here we can see, here this OD minus will abstract proton from this either of this methyl group, and it will convert into enolate. So when this enolate is falling back, it will abstract a proton from D2O, and as we have seen in the acidic condition case, if this is repeated multiple times, hexadeutyrated acetone can be recovered, right? Hexadeutyrated acetone can be recovered, right? Because in this system there is no proton available. Instead of that, whatever available is deuterium. So it will abstract deuterium when it is falling back to give this ketone. Clear?
Yes, ma'am.
Okay, so here this case also establish the existence of ketoenol tautomerism in acetone. So this is like control experiments. So the third option is when treated with dilute H2SO4 in H2O18. This acetone with O18 substitution is obtained. So as we have seen, like in this acidic condition, here instead of deuterium, there will be H plus, and when it is falling back, it is going to abstract this hydrogen. Nothing is happening with the oxygen. Like whatever oxygen we can see here in this enol form and in this ketone form, it is not changing in the system. Like only the proton is changing, like oxygen is not exchanging from the solvent or something. So this option we cannot claim is correct. See this here, oxygen anyway is not here. We can see here there will be H3O plus, and they have given this oxygen will be, this oxygen will be 18 isotope of oxygen. So when it is falling back from this enol form, it will abstract the proton only, not oxygen. So there is no chance for substitution of oxygen of this acetone with O18 isotope. So this option does not establish the existence of ketoenol tautomerism in acetone. So this will be the right answer for this question. Is this clear?
Yes, ma'am.
Okay. Now we will move to fourth question. So this is the right option. When treated with dilute H2SO4 in H2O18, this 18 oxygen substituted acetone is obtained will be the correct option for this question. We will not obtain this O18 substituted acetone. So this is the fourth question. Predict the plausible products in the following hydrate addition reaction to 2-butanol. So here it is a reduction reaction that is given. We will get from this ketone we will get alcohols when treated with lithium aluminum hydrate, and they have given four options, like only S2-butanol will be obtained, R2-butanol will be obtained, and we will obtain, excuse me, sorry. Uh, Second option is only R2 butanol will be obtained, and the third option is both S butanol and R butanol will be obtained. So here they have asked only for plausible product, not the major product, right? So we can see, according to Felkin and model, the largest or bulky group should be perpendicular to the carbonyl group. So these six are some of the following possible conformations for this carbonyl group or ketone group. So out of this, when the largest group, here the largest group is phenyl group, when it is farthest from this carbonyl group, that conformation will be more stable and facile for undergoing addition, nucleophilic addition reaction. So we can see here two conformations are there with phenyl group perpendicular to the carbonyl group, and out of these two, here here we can see uh, hydrogen only is present. We have to see about Burgee units angle. So attack will take place from either of these two positions. As I have marked in this red, I will change the color. As I have marked in this yellow, nucleophile can attack from either of these two positions. Excuse me, I will. Nucleophile can attack from this two positions. It is Burgee units angle. Like nucleophile will not attack like from 90-degree angle. Instead, it will attack in a range of 105 to 107 degree, and that angle is called Burgee units angle. So here we can see, in this conformation, nucleophile will attack from this position or this position. But here this side is unfavored because of steric hindrance from phenyl. This side will be favored because less sterically hindered hydrogen is present nearby. Whereas in this case, when we consider, these are the two positions from where nucleophilic attack can take place, and out of this, here there will be hindrance because of this bulky phenyl group, and here there can be hindrance from this methyl group. So this will be the unhindered approach of for the nucleophile to give the more stable product. So we can see lithium aluminum hydrate can attack from this less hindered side, and it will give this product. And if we redraw this Newman projection, it can be written in this form, like the phenyl group and the hydrogen group are in the plane, and when we are seeing from this top, we can see methyl groups are facing towards us. So we are looking from this direction, the methyl group and the hydroxyl group are towards us, so that can be given beta sign. Then this hydrogen and this hydrogen are facing away from us, so that can be, sorry, this hydrogen this hydrogen and this ethyl group are facing away from us. So here this hydrogen will be towards backside of the observer, and similarly is the case with this ethyl group. So when we redraw it in such a form that the longest chain will be coming in the plane of paper, it can be redrawn in this fashion. So if we rotate the single bond, this ethyl group will come to the plane, then this hydroxyl group will go behind the plane, and this hydrogen will come above the plane. So this is the major product that will be formed. But there is chance for formation of minor product also when attack is taking place, when the conformer is in this form. So if hydrate is attacking from this direction, it will lead to formation of the other isomer as well. So here they have asked for plausible products only. They have not asked for the major product. They have asked for the plausible products of hydrate addition. So it can result in both R and S butanols. So this is the right answer. Is this clear? Hello.
Yes, ma'am.
Okay. Now we will move to question 5. This is question 5. This is also similar kind of question. They have given an aldehyde adjacent to a chiral center, and they are carrying out methyl grignard reaction, and they are asking for, and they have given that it is giving X and Y, where X is a major product and Y is a minor product, and they have asked what is the major product, what is X. So this can also be dealt in the similar fashion, where we have what we have seen in question 4. So as we have seen, this is the Burgee units angle. Nucleophile will attack to the carbonyl following this Burgee units angle of 107 degree, like 107.5 to 107 degree can be the Burgee units angle. So nucleophile will attack the carbonyl following this Burgee units angle. And as we have seen in Felkin Anh model, this model is called a Felkin Anh model. The largest group is written perpendicular to the carbonyl. So the largest group in our question is phenyl group. So it can be written perpendicular to this carbonyl, and these two are the conformations which we will obtain when this phenyl group is written perpendicular to the carbonyl. And as we have seen, nucleophile can attack from both these direction. Here the black flight path is the best because it is unhindered uh, because of this small size hydrogen atom, and this side attack, it is closer to the bulky pH group, so it is less favored. Similarly is the case with these two. Here it is close to pH when the nucleophile is attacking from this direction. Here when the nucleophile is attacking, it is close to the methyl group, and because of that this attack will be less favored. So the more favored attack will be from this side where the smallest hydrogen group is present. So nucleophile will attack from this position. In our question, the nucleophile is methyl group. So methyl group will attack, and it will result in this formation of this product. Here instead of this nucleophile, we can write methyl, and this is the product if we redraw it in longest chain sequence. So here there will be methyl group. And in our question, they have given Fisher projection format. So this answer, this is the right option. This is the major product, and if we redraw it in Fisher projection format, the correct answer will be this one. If we redraw our answer, here it will be methyl group, here it will be pH, and here it will be, sorry, I have to draw in this fashion. This is pH, this is methyl group, this will be hydroxyl group, and this will be methyl group. So here we can see the R and S conformation of all these Fisher projections, and we can come to know that this is the right answer. Here we can see, compared to this, here priority 1, 2 and 3. 1, 2, 3, S conformation at the center. S conformation at the center, and here at the center 1, 2 and 3. 1 2 3. Here also S conformation. So here how we will see in Fisher projection R and S. Fisher projection we can redraw in Fisher projection we can read like we can see from this angle. This is this we can see like it is in the plane PH and OH, and both these methyl groups are facing towards us. So it can be written like this format. And if we redraw it, if we rotate it, it can be written in this format where what we have got as our product. So the right option will be, so the right option will be this Fisher projection. Fisher projection we can redraw into our normal dash wedge form, and hence we can come to our answer. Is this clear?
Yes, ma'am.
Okay. Now we can move to question number 6. There they have asked the absolute configuration of the chiral centers of starting ketone in the following reaction is. And they are asked for the configuration like R and S configuration at the center 6 and center 3 of this ketone, and they have given this is the product they have obtained. So as we have seen in our previous example, as we have seen in these cases, mostly syn product is forming. Mostly syn product is forming. Like in this example also we can consider this as R group, and we can try to find out the right option. So before that I will here already they have given the chiral center and they have given the configurations, so we can find that the R and S configuration at this center, at this 6 center. So we can give this group, this R group as priority 1, this as priority 2, and this as priority 3 according to their substitution, and hydrogen priority 4. So this is going in anti-clockwise direction. So anti-clockwise means it will be S configuration. So at 6 it will be S configuration. This is clear, right? So we can rule out the option 3 and 4. So the next two options before us is this 3. What is the configuration at the center 3? Is it R or is it S? We have to find it out based on the answer they have given. How we can approach? We can draw a Felkin Anh model and see what will be the major product they will obtain, uh, and we can see the configuration of the hydroxyl group in that major product, and accordingly we can come to know about configuration at the center 3. Is it clear? So we can draw like, actually I'm drawing it with this keypad only, it will take little time. This can be CH3, and this group we can label as R group. This is R group. So we need to know what is the configuration of this medial. Is it alpha or beta? That means it is above the plane or below the plane. So first we can consider it as beta, that is above the plane. If this medial group is above the plane, there will be one hydrogen below the plane, and if we draw Felkin Anh model, it will be like this is the carbonyl, and this R group will be eclipsing with this C, like it is antiperiplanar to this CH3. And if we are looking from this direction, this medial group, if we are seeing from this direction, this medial group will be left to us, and hydrogen will be right to us. So this is hydrogen, and this is medial. So this we can redraw into major conformation according to Felkin and model. So how it will be? Here the bulky group is R group, so that should be perpendicular to the carbonyl. So if we draw this R group perpendicular to the carbonyl, it will come like this. Also, other conformation will be when we rotate it towards this direction, R group will come here, hydrogen will come this side, and medial group will come this side. So this will give the major product. Here, according to Burgid-Unit's angle, it can attack from these two directions. Here from these two directions. But here there is hindrance because of this bulky R group, and here hindrance because of this bulky medial group. Here this hydrogen only is there. So from here the nucleophile can attack. Here it is restricted because of this bulky R group. So nucleophile will attack from this direction, and we will get the product like OH, H, CH3, and it will be R, OH, HCH3, R, medial, and here hydrogen. If we draw it in dash and wedge format, here these two medial groups are coming in the plane, and these two R groups, if we are observing from this center, R group and OH will be coming above the plane, and these two hydrogens are coming below the plane. So we can draw it in this format. Here one medial group is there. Here also medial group is there. Here this hydroxyl is coming above the plane. Here this R group will be coming above the plane. So R group is bulky group. So if we rotate it and draw, it will be, I will erase and draw the correct. It will give this R group we are bringing to the plane. Medial group will go below the plane. So the product will be R. Medial group will go below the plane. Excuse me. Hydroxyl will be above the plane and medial group will come below the plane. So when we number it, it will be 1, 2, and priority will come first to this side, then this, and then 3. 1, 2, and 3. It will be R. So the correct answer is 3R and 6S. Is this clear? You can draw the
Yes, ma'am.
Felkin Anh model and see. Like you can work it out, and if you are having any doubt regarding that, you can get back to me in the next following coming week. Okay.
Okay,
Okay,
ma'am.
ma'am.
So now coming to question number 7. Here they have asked what is the major product of the following addition reaction using Felkin Anh model, and they have given reaction with methyl lithium and water. P and Q are the two products obtained. What is the major product? That is, we have to find what is P. So we have already seen this question. We have already seen how to approach this question in previous question number 5 and 6 as well. So they have given four options like option A and B, or both the products are in 1:1 ratio and none of the above. Since there is one chiral center here, both the products are not obtained in 1:1 ratio. So the options are either A or B. We can see what is the right option based on Felkin Anh model. So this is the Felkin Anh model, and this is same as that of our question, what we have discussed in question 5. So the nucleophile will attack from the unhindered side following Burgi-Dunix angle, and Felkin Anh model we have to write the bulky group perpendicular to that of the carbonyl group. Here the bulky group is pH, so we are writing it perpendicular to the carbonyl group. And there are four possibilities for attack of the nucleophile as given here, this black one and these three yellow one, because there are two conformations where pH is coming perpendicular to the carbonyl. So there are four possibilities, and out of this is the more facile one because of unhindered approach, because of this small sized hydrogen atom. And so this will give the major product. So attack will take place from this unhindered side, and it will give this product. And when we redraw it, it can be drawn in this fashion. This we have already seen in question number 5 and 6. So what will be the right option? Here both methyl and hydroxyl group are trans to, cis to each other. And the nucleophile will be methyl group. So they have asked what is the major product obtained. So the correct answer is this cis product. This can also be written in, like if we rotate it in 180 degree, it can be written in this format. So this is the right option. Is this clear?
Yes, ma'am.
Okay. These are simple questions. These are based on Felkin Anh model. If you understand the Felkin Anh model very well, then you can solve these questions easily. So this is the eighth question. This is also based on Felkin Anh model only. So here they have Here they have given a substituted ketone, and they are treating with this nucleophile, and then they are doing TBAF deprotection. So here silyl group is there. For deprotecting silyl group we are using TBAF. TBAF is a fluoride source. For deprotecting silicon containing protecting groups we use fluoride source, and mostly we use TBAF reagent. So they are asking what is the major product that is formed in this case. This also you can solve based on Felkin Anh model. But here one more thing you have to take into consideration. Here, like we have to follow this CPLAC model. CPLAC model means a electronegative group with lone pair of electrons. It should be drawn perpendicular to the carbonyl group. Here, as we can see, here this or TBDPS group. This is called a TBDPS because it is a protecting group. This TBDPS is a protecting group, tertiary butyl diphenyl silyl, TBDPS. So this TBDPS is a electronegative protecting group. Here lone pair of electrons are present on this oxygen, so this group should be written perpendicular to the carbonyl group according to CPLAC model. So as we can see, this is another example which I have taken from Claydon. Here there is lone pair of electrons on this nitrogen. It is written perpendicular to the carbonyl group, and this our nucleophile will come and attack from the unhindered side, as we have seen in Felkin Anh model, and it will give the desired product. So, in case of CPLAC model, there is additional stability um, because of this pi star and sigma star interaction. So, we have seen this is the carbonyl group, and this is the pi star orbitals of carbonyl. We have seen that pi star have greater contribution on the carbon center than at the oxygen center. When we draw the MO diagram in the lectures we have seen, and here this is the CX bond, and this is the sigma star orbital of that CX bond. So here the pi star of this carbonyl bond and the sigma star of the CX bond, these two are the sigma star and these two are the sigma. Like where bond is formed is called sigma, and the other lobes are called sigma star. So these two orbitals can combine, and it will result in a new molecular LUMO. So this is the pi star of the CO bond, and this is the sigma star of the CX bond. It can combine and result in formation of bonding orbital and antibonding orbital. Here the bonding orbital is pi star plus sigma star. It is lower in energy. When the LUMO is lower in energy, it will be more reactive. So this species will be more reactive compared to normal carbonyl groups. So here nucleophilic attack, as we have seen, will take place on this combined orbital, and it will result in formation of the product. So you can try it out these questions using the CPLAC model, as we have seen similar examples for Felkin Anh model. This also we can solve using similar concept, and we will get the answer, and the answer is this one. This also we can draw similar to that of the Felkin Anh model. I will try to solve it out now. So this is the carbonyl, and we have seen that if we rotate this and bring if we rotate this and this, if we bring perpendicular, so this can be written, this CH3 will be in eclipsed form with this carbonyl. Then this O will be this O TBDPS. This group is called TBDPS. group will be present here, and the hydrogen will be present at this side. So this, if we draw in C-plaque model, it will be like this: CH3, OTB, OTB-DPS group should be written perpendicular to the carbonyl. TB, D, sorry, DPS should be written perpendicular to the carbonyl, and here the methyl group comes, and here the hydrogen. So following Burgide units angle, the less favored attack will be from this side. So it will attack at the center, and we will get OH, CH3, and here our nucleophile is this group. So here anion will be generated, and it will attack from this side, and we will get this product. Here OTB DPS will be there, OR we can write, and hydrogen will be there, and methyl will be there. So if we redraw it into this dash and wedge format, this will be the right answer. Is it clear? Hello? Here we are following C-plaque model when there is an electronegative group adjacent to this carbonyl group. Electronegative group, or groups with lone pair of electrons are adjacent to the carbonyl group, it will follow C-plaque model. It is also similar to that of Felkin Anh model, but the difference is that this electronegative group that we will draw perpendicular to the carbonyl group, and then similar to Felkin Anh model, we will see like from which side following Burgide units angle, the attack will be very facile, like unhindered attack will be more facile. So here the attack will take place from this direction, and it will give this product. If we redraw this product, uh, it is similar to this one, so the right answer will be this one. So I hope question 8 is clear. Can I move forward? Hello?
Ma'am, I
ma'am.
have a doubt, ma'am.
Okay.
Ma'am, which group is
Hmm.
adjacent to the carbon?
Hmm.
Then Siplak model is
Okay, okay. Like this
favored, ma'am.
group, if electronegative group like chlorine, bromine, like those groups having lone pair of electrons. Here, this oxygen, this protected oxygen group, OH group is having lone pair of electrons, right? So
Yeah, ma'am.
such groups we should for such models, for such systems we should follow C-plaque model. So here this group we will write perpendicular to that of the carbonyl. So this group is called the TB-DPS group, tertiary butyl diphenyl silyl. So that group we will write perpendicular to the uh, carbonyl group as I have shown here. And then we will follow similar pattern that we are following in Felkin Anh model. Is it clear?
Okay, ma'am.
Okay. Now we will move to question number 9. So here they have asked what is the major product formed in the following reaction, and here they have given like a similar substrate for C-plaque model, but here there is one difference, or one, what we will say, like this system will not exactly follow the C-plaque model or Felkin Anh model. That is because of chelating effect from the Zn2 plus ions. So we can see what will be the right answer for this question. So we have seen that there will be a reversal of selectivity. We have seen like a selectivity for non-chelated Felkin models with ions like Na plus and all. So if there is chelation possibility, that selectivity will be reversed. So here, if attack is taking place in case of this NaBH4, the ion formed will be Na plus. It cannot have chelating effect. Then it will follow Felkin model, and it will give this as the major product. But in case of this uh, magnesium, magnesium have the power to do chelating effect. So it will chelate that group, this OMe group, and because of that it will not exactly follow this Felkin model, and we will get the opposite isomer as the major product. So for chelation, two things are necessary: a heteroatom with lone pairs available for coordination to a metal. So, in our question, we are having that such a heteroatom. Like with this ketone, there is one heteroatom that can coordinate with the metal, and a metal ion that prefers to coordinate to more than one heteroatom at once. So here, if we have more charged ions, they can coordinate with more than one heteroatom. Like we can see this magnesium have 2 plus charge, zinc have 2 plus, copper 2 plus, titanium having 4 plus charge, cerium having 3 plus charge. Such ions can chelate with more than one heteroatom. So when these metals are present in the system, there is chance for chelation, and there is necessary for one heteroatom having lone pairs to coordinate with the metal. Here, this oxygen also this oxygen have are having lone pair of electron. It can coordinate with the metal ion, and it will result in chelation. So it will give the opposite isomer. We can see how. So this is an example similar to our question. So this is the Felkin model that as we have seen. Sorry. This is the Felkin model as we have seen, where nucleophile will attack from the unhindered side, and it will give this major product. When there is chelation, we cannot write this OR group perpendicular to the uh, carbonyl. It will be chelating with this metal, and attack will be taking place from this direction. Here the methyl group will be considered as the bulky group. So we will obtain the other product, other isomer as the major product. Is this clear? Because of chelation effect, as we have seen in the previous example, when lone pair of electrons are present in the system, we have seen that that should be written perpendicular to the carbonyl group. But in this case, since the metal ion Mg2 plus, it can coordinate with that two heteroatoms, that is this oxygen and that of OMe. It can coordinate with both this oxygen atom. Then this OR cannot come perpendicular to the carbonyl, and the other second medium bulky group, that is the methyl group, will come perpendicular to the carbonyl, and nucleophilic attack will take place from this direction. So we will get the other isomer as the major product. Is this clear?
Yes, ma'am.
So like in our previous cases and all, whatever metals were present, they are non-chelating kind of metals. So here in this question, they have given ZnBH4 twice. So here Zn 2 plus ion will be formed. So and because of that, whatever Felkin model product we are getting, its opposite isomer will be the major product, as we can see here from this example. According to Felkin model or CPLAC model, we should write this electronegative group, or this atom containing lone pair of electrons perpendicular to the carbonyl group. But here In this case, because zinc is having 2 plus charge, it can coordinate with these two heteroatoms, and uh, whatever expected product we cannot get, like we cannot write it in perpendicular format to that of the carbonyl, so we will not get this expected product. Instead we will get its other isomer. So here whatever product we are getting is this one. According to Felkin model, we are supposed to get this product, but because of chelation effect from this Zn2 plus, we will get this as the major product. Is this clear? Hello? Hello?
Yes, ma'am.
Okay. So now we will move to question number 10. Here they are asking how many tautomers can be drawn for the following ketones. So for ketoenol tautomerism to take place, there should be presence of one alpha hydrogen atom. So in this case, there are two alpha hydrogen atoms present. So if abstraction of proton is taking place from this side, it will give one tautomer like this: ketone, double bond, OH, and isopropyl group. This is double bond. If abstraction of proton is taking place from this side, it will give this tautomer: OH, double bond. So the correct answer will be 2. Two tautomers we can draw. As we have seen here, one tautomer will be because of abstraction of this alpha hydrogen, and the second tautomer will be because of abstraction of this hydrogen. So the correct answer is 2. Is this clear?
Yes, ma'am.
Okay. Now we will move to our last question. It is similar to whatever first three questions we have seen. So which of the following has greater enol content than the keto counterpart? So here they have given one ketone, here one aldehyde, here a diketone, and here one ketone with two isopropyl substitution. So as we have seen in the previous case, here in this case there will be more resonance stabilization compared to all other case where there is single ketone. Here when an anion is formed here, it can resonate to this side as well, this side as well. So here more resonance stabilization will be there, and because of that here the enol content will be more. Also here when an enol is forming on one side, it can form hydrogen bonding interaction with this ketone, forming a six membered transition state. Six membered, it can result in a six membered system, and because of that this will be giving enol content more. So our correct answer will be this one. Is this clear?
Yes, ma'am.
This is similar to our first two questions. First two questions we have seen like what all are the factors that influence in enol formation more. So here hybrid because of resonance effect and because of this hydrogen bonding factor, this will be the correct answer because it will give enol content more. So this was the last question in this assignment. Do you have any doubt regarding any of the questions? I hope it is clear for everyone. So thank you for attending this session. We can meet in next week at the same time from 6 to 7 on Tuesday. Thank you.
Thank you, ma'am.